Hello and welcome to the Unit 2 podcast on Section 6.1, the development and history of the modern periodic table. So I'm Mr. Sakaguchi,
And I'm Mr. Lin.
and today we're going to talk a little bit about the periodic table as a whole.
Yep.
Did it again to me. There we go. I don't know why it does that. Antoine Lavoisier was known as the grandfather of chemistry. Back in his time in the 1790s, there were only 23 known elements, so there wasn't a whole need for predicting or organizing the elements in any kind of fashion. But as time went on, as technology began to catch up, more elements were discovered. Some of these elements were discovered because of technology jumps. Electricity was invented, and they were began to apply that not only into subatomic particles, but also to break down compounds into their constituent elements.
And at this point, industry was pushing itself to use resources better, or to understand the use of resources better. And as a result, organizing the elements that were newly discovered at this time was pretty necessary.
Yeah, so as the industrial age kind of moved on, the need for better materials for whatever was being built became more important. And so more about chemistry needed to be known. And as this data emerged and as more elements were discovered, there became a need to kind of organize these elements in a way to see which elements had things in common, which ones didn't, to kind of help organize the elements as a whole. The first person to really try and attempt this was a fellow by the name of John Newlands.
The big thing that he noticed was that certain elements repeated properties every 8 elements. And since he was a musician also, he called this the law of octaves. As a result, he organized it in a fashion where certain elements were lined up in the same column, and they also were organized in other fashions, such as by mass. His law of octaves wasn't fully accepted quite yet because it still had discrepancies with it, and it didn't do the best job of predicting things. There were still too many exceptions to his rule.
Also, the science community didn't really like the music reference, as chemistry was still trying to kind of carve its way out as a legitimate science and kind of leave the whole alchemy thing from the Dark Ages. A better attempt was done independently by 2 different guys. One was Lothar Meyer and one was Dmitri Mendeleev, and they basically came up with the periodic table you see on the right here. So this was Mendeleev's periodic table when he originally published. Mendeleev was actually writing a textbook for his students at the time, and so he was organizing the elements in a way that he could try to best explain them to students, much like yourselves. And so he basically created columns and rows, and basically increasing mass were the columns, and then similar properties is what put them in rows.
Now, the big thing about Mendeleev, and the reason he got more credit for his periodic table, was because he left blanks in it for predicting future elements that hadn't even been discovered yet, and also predicted the properties that these undiscovered elements would possess. And when they finally did find them, he came pretty darn close. And this gave more weight and credence to Mendeleev's periodic table.
So this is why you see Mendeleev getting the majority of the credit, whereas Meyer kind of gets lost in the shuffle. Very similar to like DNA and Rosalind Franklin. And Mendeleev's table was the table until the early 20th century, and as more began to be known about the subatomic properties of elements, stuff we actually talked about in the last unit, a reorganization of the periodic table emerged, led by Henry Moseley. He reorganized the periodic table based upon not increasing mass, but increasing atomic number. And you guys know from Unit 1, atomic number is the number of protons. So the rows were based upon atomic number, and the columns were similar properties. This also gave idea to the periodic law, and this is an idea that certain properties will steadily increase or decrease as you move from left to right across a row.
There was also a grouping of the of the elements in a fashion similar to what Newland's proposed in his law of octaves, and because certain elements were arranged so that the ones that had similar properties were all lined up in the same vertical column.
Also,
So you see influence from there.
yeah, also one of the reasons why Mendeleev's table needed to be kind of worked on a little bit is that there were some slight discrepancies in his table as well. Areas where um, elements were kind of or weren't in the right spot, and finding atomic number kind of helped mediate that.
So you would notice, you can look it up on your own periodic table. You'll notice sections where one element's got a lower atomic mass but a higher atomic number, and they get switched around a little bit. That was where Moseley found the discrepancies and fixed that with organizing it by atomic number instead.
So now we're going to switch gears a little bit and move away from the history lesson and talk more about the features of the modern table. So what you see here on the left are periods. Periods are horizontal rows. Groups are vertical columns. Occasionally groups will be called families as well. Groups are numbered in two different forms. In this particular periodic table, the groups are numbered 1 through 18. Also, you'll see numbers and in either an A or a B in front of them, so you might see a renumbering or a numbering in Roman numerals above. The periods are also numbered from 1 to 7, and later on we'll learn that is closely related to principal energy levels. I'll let you do this one.
Okay, so the elements can be classified, shown here, in different vertical columns or just different groups in general, and they have similar properties. So you've got your alkali metals here in your group 1. It's also sometimes called 1A, and then you've got your second group, 2A, and then you've also got 8A as well, and 9A. They're colored similarly because they share similar chemical properties. You've got this magenta section here in the middle called the transition metals, and then an insertion here around element 57 and 89. That actually is a lead into this lower section called the rare earth elements, and they slide inside of that transition metals.
Yeah, so notice the jump in atomic number from 57 to 72 and 89 to 104. Sometimes these are also individually referred to by period as the lanthanide and actinide series. One other thing to note is that hydrogen, even though it's in group 1A, is not an alkali metal.
Right.
And this is group 7A. And most of the periodic table, if you look at this closely, is mostly metal. We also have metalloids in yellow. Metalloids represent elements that have properties of both metals and nonmetals. So if you look at this periodic table, a lot of it is all metal, right, and the majority are metals, whereas very few are actually nonmetals. Other things to note is that, as we said earlier, some of the if we group up elements together, groups 1A to 8A would be the representative elements. So in a different numbering system, this would be group 1A, this would be group 2A, 3A, 4A, 5A, 6A, 7A, and 8A. So those are the representative elements. The transition metals are numbered Bs, 1B to 10B.
And that numbering's moved around a little bit differently too, so don't worry about that.
Right, whoops, wrong way. We also have the intertransition metals, again, is another way to refer to them as opposed to rare earths. Some of these we already talked about. Alkali metals, again, is group 1A, not including hydrogen. They're the most reactive group of metals, and they're never found pure in nature. Right. Alkaline earth metals are group 2A. They're the second most reactive group, and they're not found pure in nature either. We have our halogens in group 7A. They're the most highly reactive group of nonmetals. And noble gases are unreactive or rarely reactive. In terms of metals and nonmetals, this is a kind of a summary of their properties. Notice that metals are always solids with the exception of mercury. Right. They're shiny and smooth, which means sometimes they have what we call luster. They conduct heat and electricity very well. They're malleable, which means you can pound them into sheets, and ductile, which means you can draw them into wire. Gases, nonmetals can exist in all three states. They can be solid, liquid, or gas.
But one thing they definitely are poor conductors of heat and poor conductors of electricity.
And then your metalloids, these are elements that have a mix of properties depending upon which metalloid we're talking
They
about.
kind of pick and choose from both categories, depending.
And
That's pretty
until
much
next
it.
time.